Welcome to AP Statistics. Today we are diving into topic 2.7, Residuals and Residual Plots. By the end of this lesson, you will be able to represent the differences between measured and predicted responses and use residual plots to describe the form of association in bivariate data. The core of this topic is the residual. A residual is simply the difference between the actual observed value, which we call y, and the predicted value from our regression line, which we call y hat. A helpful way to remember this is AP, actual minus predicted. If a data point lies above the regression line, the actual value is greater than the predicted value, resulting in a positive residual. If the data point is below the line, the actual value is less than the predicted value, giving us a negative residual. And if the point is exactly on the line, the residual is 0. Let's look at an example. Imagine we have a model predicting exam scores based on hours studied. Our model is y hat equals 60 plus 5x. Suppose student A studied for 4 hours and got an 85%. First, we find the predicted value. 60 plus 5 times 4 gives us a predicted score of 80. Now the residual is the actual score, 85, minus the predicted score, 80. The residual is 5. This means student A scored 5 points higher than our model predicted. Now that we understand what a single residual is, let's look at how we visualize all the residuals for a dataset at once, using a residual plot. Our goal here is to determine if our chosen model, usually a linear one, is actually the best fit for our data. A residual plot is a scatter plot where the horizontal axis represents the explanatory variable, x, and the vertical axis represents the residuals. Essentially, we are taking the regression line from our original plot, turning it horizontal, and looking at how far each point sits above or below that line. The horizontal line at 0 represents the regression line itself. Points above this line have positive residuals, and points below have negative residuals. When we look at a residual plot, we are looking for one specific thing: randomness. If the points in the residual plot are randomly dispersed around the horizontal line with no clear pattern, then a linear model is appropriate for the data. Think of it this way. If our linear model is doing its job well, the only thing left over should be noise or random chance. If there's no pattern in the leftovers, then the straight line captured the main relationship perfectly. What happens if a linear model is not the best fit? We use residual plots to investigate the appropriateness of our model. If you see a clear, non-random pattern in your residual plot, it is a major red flag. Suppose we have data that actually follows a curve, but we try to force a straight line through it anyway. Look at the resulting residual plot. Notice how the points aren't random? They form a clear U-shape or a curve. When you see a pattern like this, a curve, a wave, or a fan shape, it tells us that the linear model is not appropriate. The leftovers still contain a predictable shape that the straight line failed to capture. In AP Statistics, this is the most common way to justify using a different kind of model. If the residual plot has a pattern, the linear model is a poor choice, even if the correlation coefficient, R, is relatively high. To recap, random scatter means the line is good. A clear pattern means the line is bad. Always check your residual plot before trusting your linear regression results. You have now mastered the basics of residuals and how to interpret their plots.